For homework 4, part C, we're going to be using the final value theorem in order to show that a second order system with the PI controller will always reach its desired set point. So the first thing we want to do is define our control output from our PI controller. So our C is going to be equal to our KC times our air plus 1 over tau I times the integral from 0 to t of our air d tau I. And taking the Laplace transform of this, we get our big C is equal to Kc times big E plus 1 over S tau I times big E. And it's important to note that our control output is equal to our air, so our big E times our GC is equal to our C. So our GC would be this divided by E, giving us our GC will be Kc plus Kc over S tau I. So the next thing we need to do is determine our closed loop function, which we know our shortcut for determining the closed loop is what's on top. So our GC times GP over 1 plus GC times GP times GM times our YSP, our set point, is equal to our big Y. Okay. So next, we need to substitute in our GCs and GPs and GMs, and we know our second order transfer function or process function will transfer process something. Second order process transfer function is going to be K over tau S plus 1 squared. It's also important to note that this can be simplified to GC is equal to KC times 1 plus S tau I over S tau I. And now we can start plugging in our GCs, our GPs, and our GM, which are measurement. In this case, our GM is just equal to 1. So we get Y is equal to GC, so KC 1 plus S tau I over S tau I times our GP, so K over tau S plus 1 squared over 1 plus GC, so 1 plus S tau I over S tau I times GP K over tau S plus 1 squared, tau S plus 1 squared, times our GM, which is just 1, times our YSP, set point. So this now becomes just our GCO, our closed loop. So now we can move on and do our final value theorem analysis. So our limit as S approaches 0 is equal to our Y at infinity. And to do our calculation, we will need our limit as S approaches 0. So we'll have limit as S approaches 0 our S times GCL times our A over S, which A over S is representing our set point and our time step, and this is equal to our y at infinity. So now we need to evaluate our GCL as our S approaches 0. So for our tau S plus 1s here, these are going to become 0, 0, giving us times k, times k. This 1 stays 1, gets cancelled out. So what we end up with is just, and then these s's here will become 0, and these s's here will become 0, but these need to stay because that will create a situation in which we are going to infinity. So what we end up with is our GCL as S approaches 0 is Kc 1 over S tau I times K over 1 plus 1 over S tau I times K. We are missing the Kc right here. So there should be another Kc with this 1 plus S tau I. So times Kc. Now if we plug that back in as our S approaches 0, these S's will cancel out, giving us just our GCL times A is equal to our y at infinity. So we have limit as S approaches 0. We have Kc 1 over S tau I times K over 1 plus Kc 1 over S tau I times K times A. So as our S approaches 0, 1 over S tau I. So as S approaches 0 for 1 over S tau I, we know that this goes to infinity, meaning that this will end up as infinity over 1 plus infinity, which simplifies to 1 because the 1 will be negligible at a scale so large, meaning that our limit as S approaches 0 is just going to be equal to 1 times A, which is just equal to A. So A being our original set point will always be equal to y at time of infinity, meaning our system, our second order system with a PI controller will always reach its desired set point. For the next part of homework 4, part C, we're going to be looking at a system with an inverse response and a proportional only controller. So we know for our inverse response, our GP is going to be equal to, our K1 over tau 1 S plus 1 minus K2 over our tau 2 S plus 1, which simplifies to K1 tau 2 S plus 1 minus K2 tau 1 S plus 1 over tau 1 S plus 1 times tau 2 S plus 1. Now, multiplying this out, we get tau 1 tau 2 S squared plus tau 2 S plus tau 1 s plus 1 on the bottom. So we can then move on. So we know that our GC for a proportional only controller is going to be equal to KC. And then using our shortcut to determine our full system, we know our Y is going to be, or our GCL, or closed loop, is going to be equal to our GP times our GC over 1 plus GP times GC. So what we end up with is, for our closed loop, is KC times K1 tau 2 s plus 1 minus K2 tau 1 s plus 1 over tau 1 tau 2 s squared plus tau 2 plus tau 1 times s plus 1 over 1 plus KC K1 tau 2 s plus 1 minus K2 tau 1 s plus 1 over tau 1 tau 2 s squared plus tau 2 plus tau 1 times s plus 1. So that will be our GCL. And what we can do one more time is simplify this further by dividing across and getting a common denominator of our polynomial. So what we'll end up with for our final GCL is KC times K1 times tau 2s plus 1 minus K2 tau 1s plus 1 over tau 1 tau 2s squared plus tau 2 tau 2 plus tau 1 times s plus 1 plus KC times K1 tau 2 s plus 1. This needs a big parentheses and another big parenthesis here, minus K2 tau 1 s plus 1. We then need to combine all the terms with s in our bottom. So we can see we start with our tau 1 tau 2 s squared plus parentheses. Now we have tau s plus 1. So we'll multiply that out, giving us KC K1 tau 2s plus KC K1 and also minus KC K2 tau 1 s minus KC K2 multiplied here. So what we end up with here is tau 2 plus tau 1 plus KCK1 tau 2 minus KCK2 tau 1, and this is all multiplied by S. So we got rid of this, we got rid of this, and that counts for this entire term. So now we move this over, we move this over, so all we have left is R plus 1 plus KCK1 minus KCK2. Okay, and that will be what's on our bottom with all of our S's separated. Using our Van Neumann stability analysis we used previously, where did that go? So we know our an minus 1, an minus 2, an minus 3. So we'll move our terms into this form, or our Roth-Howitz, not Van Neumann, Roth-Howitz stability. So our first term, an, is going to be tau 1, tau 2. Our second term is going to be tau 2 plus tau 1 plus KC K1 tau 2 minus KC K2 tau 1. Our third term is going to be 1 plus KC K1 minus KC K2. And our last term is going to be 0 in this spot. We then need to get our, did I scroll past again? We need to get our Bn and our Cn. So an minus 1, an minus 2. So that gives us our tau 2 plus tau 1 plus Kc times K1 tau 2 minus Kc times K2 tau 1 times 1 plus Kc K1 minus Kc K2 minus our an and an minus 3, which in this case is going to be 0 because our an minus 3 is 0. And this is all divided by an minus 1. So we divide this by tau 2 tau 1 plus Kc K1 tau 2 minus Kc K2 tau 1, which these cancel out, leaving us with our Bn equal to 1 plus KCK minus KC K1 K2. So that would mean our next step is to get our Cn. So our Bn times an minus 3, an minus 1, Bn plus 1, which is just going to be 0 because our Bn plus 1 is also going to be 0. So what we know is we need there to be no sign changes, so our Bn must be greater than 0, meaning all we have to do now is we can simplify this to 1 plus Kc K1 minus K2, and we can move our 1 across to the other side. Giving us our Kc times K1 minus K2 is greater than negative 1. And then to solve for Kc, we can just divide across by K1 minus K2. So our Kc must be greater than negative 1 over K1 minus K2. In our situation, our K1 is 2, so K1, and our K2 is 1. So what we end up with is our Kc must be greater than minus 1 over 2 minus 1, or Kc must be greater than negative 1. So what we can also look for is another situation that constrains it. So this is another equation we can use, because this sign, since this is positive, this must also be positive. So we can use this to find our upper limit for Kc. So if we pull out our Kc's, we get tau 2 plus tau 1 plus Kc times K1 tau 2 minus K2 tau 1 is greater than 0. If we take this, subtract it across, we get our Kc times K1 tau 2 minus K2 tau 1 must be greater than negative tau 2 plus tau 1. So now we can solve these for our givens. So our tau 1 is 10, our tau 2 is 2. So we'll write that down. Tau 1 equals 10, tau 2 equals 2, K1 equals 2, K2 equals 1. So what that gives us is, we get our K1, so 2, times tau 2, so 2 again, minus K2, so 1, times tau 1, so 10, so we have minus 6. Kc times minus 6 is greater than minus tau 2, so 2, plus tau 1, so 10, minus 12. So we get Kc times negative 6 is greater than negative 12, and dividing across by negative 6 with the negative sign gives us Kc must be less than 2. So from our Rath-Howitz stability analysis, we know that our Kc value for this given system must be greater than negative 1, but less than 2. For the last part of homework for part 3, we're going to be using Python to check if our analysis of the stability of our inverse response system is accurate. So we're going to be using something similar to what we did in the last part. So we'll start by copying this over. We need to run these quickly, and while that happens we can go back. So we don't need any of these for our system, and we know that our Kc in this case must be greater than negative 1, but also less than 2, and this is what we'll be testing. So our GC, oh this isn't right, it should be our GP, and this will be our GC, which is just equal to our Kc value. So we'll start at a value that's within our range, so 1, and we know our GP in this case is going to be, we can check our process, so 2 over 10s plus 1 is equal to 2 divided by 10s plus 1 minus 1 divided by 2s plus 1. So that is our process transfer function. I don't know why it's giving me not closed. These should all be closed. closed, closed. We don't need this. Okay. It's being weird. Anyways, so we'll call this our GCLI for our inverse relation. It's going to be our GC times GP, 1 plus GC times GP. So we can try and run this. Decimal multiplied by, so that works. We'll be using the same type of function as the last one. We need to update which function we're using. We're going to be using GCLI and then simulating this the same way. A is not defined. Do we need an A? I guess we'll call our set point A is equal to 1. Sure. And same thing here. As you can see, this system is stable, and it goes down, it goes up, continues on, and reaches stability. So now, as we change our value of Kc, we should notice that as it approaches numbers like 2 or -1, there seems to be more variation in our stability. And then if we are to surpass one of those bounds we found, we see that our system becomes unstable and our error continues to grow exponentially. So that is testing our our limit, our upper bound of 2. So we'll put it right at 2. And as you can see, no stability. And if we go just below 1.99, it eventually becomes a stable system. And now if we take it to our other limit of -1, -0.99, see that this is kind of like a logarithmic scale. It's kind of hard to tell with this one, but if we go to 0.9, you can see that eventually it reaches a steady state. However, if we go to -1.1, you can see that this begins to grow exponentially instead of decay. So using that, we can see that our limits that we determined using our Routh-Howitz analysis do hold up in our Python simulation.